Here's a problem. We are going to solve it all the way by hand. This tank has a level in it. Right now the level is 4. Shut the valve completely, hands off, and the level slides down on its own, all the way towards 0. That's what x dot equals minus x means. Left alone, the level always falls back toward nothing, at a rate equal to how much is left. But you have a valve. Push on it and you feed the tank against that drain. That's your control, U. Two things are being scored. At the final bell at t equals 1, we measure how far the level still is from 0. That's the red bar. And all the way along, we charge you for effort, half u squared, piling up in the pink bar. Add them and you get the score J. So here's the ask, not a number, a whole curve. Find u of t for every instant between 0 and 1 that makes j as small as it can be. No theory yet, just the problem. Your first instinct is to guess. So let's guess. Hold the valve at 0 the whole time. Then the tank just drains. X is 4e to the minus t. And at the bell, that's 4 times 0.368, which is 1.472. Square it for the miss, 2.165. Effort spent? Nothing, because we never touched the valve. So the score is 2.165 and you just computed it yourself. Try 1. Worse, 4.925. Try minus 1, pulling the level down hard, 1.205. Try minus 2, 2.043. We overshot. Best of the 4 is minus 1 at 1.205. But watch this one. It scores 1.1613, better than every one of them. And notice it isn't flat, it bends. That's the trouble with guessing. A constant has one knob. A curve has a knob at every single instant, infinitely many. You'll never guess your way onto it. What we need is a rule that takes any curve at all and hands you back a better one. Let's build that rule. To build it, we need one idea from chapter 5, the price of being somewhere. Along the way, you are paying, instant by instant, half u squared, that pink area piling up under your control curve. But there's a second thing you are paying, and it's hidden. Being at a level x right now changes what you can score later. Call that price P, the co-state, what one extra unit of level is worth to your final score. Put the two together, the cost you pay right now plus the price times the motion you're buying. For our tank, that reads H equals half u squared plus P times, in brackets, minus x plus u. That object is the Hamiltonian. And written in general, it's the same two pieces, the running cost G plus the price vector P dotted with the motion A. Out of that one object fall three conditions the best path has to obey. The state moves along the slope of H in the P direction. The co-state moves along minus the slope in the X direction. And the control sits where the slope of H in the U direction is 0. 3 rules. We are not deriving them today. We are going to use them. So use them. Lay the rules on one clock, running left to right. Blue lane on top for the state. Violet lane underneath for the co-state. To integrate anything, you need a complete launch state at the left edge. Look at what we actually have. At the start, we know the state. X at t0 equals x0. That end locks green. At the finish, we know the co-state. P at tf is pinned by the final cost. That end locks green too. But the other two corners are question marks. The starting co-state, unknown. The final state, unknown. Watch the playhead try to march forward from the left. It reaches the gate and it stalls. It can't even begin because the violet lane has no launch value. Half the story at each end and neither end is complete. That's the wall. You can't press play. Forget trajectories for a minute. Forget control theory entirely. Here is a hill, two knobs, and a height that depends on both. Drop a ball anywhere on it. At that point, there's exactly one direction where the ground climbs fastest, the gradient, pointing straight uphill, square to the contour. So walk the other way, step against the gradient by some amount tau, and you must go down. Keep stepping and you land on the valley floor, exactly where the slope dies out to zero. One thing can ruin this, and it's the size of the step. Too big and you fly across the valley onto the far wall, then back, zigzagging forever. Too small and you'll spend the whole afternoon measuring slopes instead of walking. Get it right and the descent is clean. And here's the guarantee that makes it honest. The change in height is minus tau times the size of the gradient squared. That's a negative number. Downhill is downhill. Now the leap. On the hill where we stood was a point, two coordinates, two little bars. But in a control problem, the thing we choose isn't a point, it's a whole curve. So watch the two bars multiply. 10 of them, 100, one for every instant along the teal time axis, and their heights joined up are an entire pink control curve, u of t. The hill is still a hill, but now its height is the cost of the whole curve, j of u. So what's the gradient of that? It has to be a curve too. Here it comes, in red, underneath the pink one, dh by du at every instant. One slope per moment, a profile of blame, telling each instant of your curve how much it's costing you. And the correction is one synchronized nudge. Every point of the pink curve slides down at once, each by tau times the red height beneath it. New curve equals old curve minus tau times dh by du. And the change in cost is minus tau times the size of that red curve squared. Negative, always. But where does the red curve come from? This is the beautiful part. Take your current guess for the control, any guess. Start the blue state at the green x0, which we know, and integrate forward left to right. Store the whole path and notice what storing it just bought us. We now know where the state ended up. That matters because the co-state's terminal value is the final cost differentiated at that ending state. A moment ago, it was a formula with an unknown in it. After the forward sweep, it's a number. Green, known. Start there and integrate the co-state backward, right to left. And as the violet dot sweeps home, the red gradient curve paints itself underneath, instant by instant. Now notice what we never did. The starting co-state, the missing corner, the thing that stalled the playhead, we never guessed it, not once. The wall isn't smashed, it's sidestepped. 6 steps and that's the whole recipe. Write h, take the 3 derivatives, guess u and sweep the state forward. Sweep the co-state backward, read the red curve, nudge and repeat. That card stays with us now. Let's go solve our tank. Steps 1 and 2. Write the Hamiltonian for this problem. The running cost is half u squared, and that term flies straight out of the pink effort meter. Then the price times the motion, p times in brackets minus x plus u, and that one comes out of the tank's own motion arrow. So h equals half u squared plus p times minus x plus u. 3 derivatives, and we take them by hand. Differentiate with respect to u. The half u squared gives u, the pu gives p. Everything else has no u in it, so it grays out. dh by du equals u plus p. Next, with respect to x. The only x is inside p times minus x, so dh by dx is minus p. And the rule says p dot is minus that, so p dot equals plus p. Watch what that means. the violet costate grows to the right. Finally, the terminal cost, the bit we pay at the bell. That cost is x squared at 1. Differentiate it with respect to x and you get 2x. So the costate at the end, p at 1, is 2 times x at 1. Steps 1 and 2 ticked. Step 3, guess. And we'll take the laziest control there is. U equals 1 everywhere. Yes, the same flat one that scored worst in the lottery, 4.925, on purpose. Watch the loop dig it out. Put it into the plant and you get x dot equals minus x plus 1, starting from 4. Solve that with the picture, not a formula. Ask, where would the level sit forever and never move? Set x dot to 0. Then x equals 1. There's our resting level, the green dashed line. We start at 4, so the gap between where we are and where we settle is 4 minus 1, which is 3. And a gap like that decays like e to the minus t. So x of t is 1 plus 3 e to the minus t. Check it. At t equals 0, that's 1 plus 3, which is 4. Correct. Differentiate it. X dot is minus 3 e to the minus t, and minus x plus 1 is exactly minus 3 e to the minus t. Correct. So draw it, the blue curve falling left to right. And where does it land? 3e to the minus 1 is 1.1036. Add the 1, x at 1 is 2.1036. Green dot. Step 3 ticked. Step 4. And now we work from the right. We know p at 1 is 2 times x at 1. We just computed x at 1, 2.1036. Double it, 4.2073. That's a green dot at the right hand end of the violet lane. Next, p dot equals p. Read that literally. This thing's rate of growth equals itself. Only one shape does that, e to the t. So p of t has to be some constant times e to the t. And we have exactly one fact to pin the constant with. At t equals 1, p is 4.2073. Write it in the form that makes that obvious. P of t equals p at 1 times e to the quantity t minus 1. Because at t equals 1, the exponent is 0, e to the 0 is 1, and we land on 4.2073 by construction. Now simplify. E to the minus 1 is 0.3679. And 4.2073 times 0.3679 is 1.5478. So P of t is 1.5478 e to the t. Draw it right to left. It lands at P of 0 on that same constant. Step 4 ticked. Step 5. Read the red curve. We already know dh by du equals u plus p. So this is just addition. And we can do it on the picture. Stack the flat pink one on top of the violet costate, instant by instant, and the red curve paints itself. 1 plus 1.5478 e to the t. Now read it off. At t equals 0, the pink guess is 1, and the costate is 1.5478, which the table rounds to 1.548. Stack them. 2.548. At t equals 1 half, the guess is still 1, and the costate is 1.5478 times e to the 1 half, that is times 1.649, which gives 2.552. Stack them, 3.552. At t equals 1, 1 plus 4.207 is 5.207. 3 dots landing on the curve. Now look at that curve and tell me what it says. It never touches 0. It's positive everywhere and growing. Positive slope means pushing u up costs you more. So u is too big, not somewhere, everywhere. Down arrows all along the flat guess, biggest at the end. Step 5 ticked. Step 6. The correction. Set the step size dial to tau equals 0.1. New u equals old u minus tau times the red curve. Substitute it in. u1 of t equals 1 minus 0.1 times, in brackets, 1 plus 1.5478 e to the t. Multiply through. A tenth of 1 is a tenth, so the flat part drops from 1 to 0.9. And a tenth of 1.5478 is 0.1548. So u1 of t equals 0.9 minus 0.1548 e to the t. Evaluate it at 3 instants. At t equals 0, e to the 0 is 1. So it's 9 tenths minus 0.1548, 0.745. At 1 half, e to the 1 half is 1.649 and 0.1548 times that is 0.255. So we get 0.645. At t equals 1, e is 2.718 and 0.1548 times that is 0.421. So we get 0.479. Notice the subtraction grows as we go right. That's the bend arriving. Each value pulls its point of the flat line down by exactly the arrow we drew a moment ago, and the line droops toward the end where the blame was heaviest. Step 6 ticked. 1 full lap. Did it actually work? Let's do the scoreboard by hand. And you've seen the first number before. The old control was the flat one, and in the guessing lottery, the flat one scored 4.925. Here's where that came from, and it's the same 2 bars we drew in the very first shot. The red one, the miss at the end. X at 1, 2.1036 squared, which is 4.4253. The pink one, the effort, 1 half times the integral of 1 squared from 0 to 1, which is just 1 half. Add them, 4.9253. Now rerun step 3 with the bent control. Same equation, same starting 4, but u is smaller, so the blue curve redraws lower and lands earlier. X at 1 is 1.8585. Read it off the new green dot and square it, 3.4541, a full point below the old miss. The effort is the pink area under the bent curve. That integral is the one piece here you'd reach for a calculator on, and it comes to 0.2039, well under the half we were spending because we are pushing less. Add them, 3.6580, 4.9253 down to 3.6580. The mismatch meter drops to about 74% of where it was. Is that optimal? No. Is it strictly better? Yes. And one area aside, you could redo every line of that on paper. Do it again. And again. Watch the pink curve on the left as the laps go by. It sinks, it flattens, it crosses 0, it goes negative, and it settles into a shape. And that's your stopping rule, by the way. You don't stop when the picture looks nice, you stop when the red curve is small. Measure its size, and when it drops below a tolerance you chose in advance, the slope has died out and you're on the floor. It's the same test as the hill. 0 slope, valley bottom. On the right, the score, 1 lap at a time. 4.925, 3.658, then 2.8, 2.3, 1.9, 1.6, and on and on. Notice the personality of that staircase. Big drops first, then a long crawl. Eventually, it comes to rest at 1.1613. Now this particular problem happens to have an exact answer you can write in closed form. U star of t equals minus 0.5806 e to the t. There it is, in gold. laid on top of our converged pink curve. They're the same curve. And that's the point. We never needed that formula. Sweep, sweep, read, nudge. The loop found it. New problem. Same 6 steps. The recipe card unticks. You're holding a position and you have to be out of it by the closing bell. The blue bar is your inventory, Q, starting full at 1. The pink lever is how fast you sell, U. So Q dot equals minus U. 3 forces are pulling on you. Sell fast and you move the price against yourself. That's impact, the pink area, U squared. Sit on it and you carry risk while the market moves. That's the blue shading, 0.1 Q squared, growing with how much you still hold. And whatever is left at the bell gets slammed out at a penalty, 10 Q squared at 1, the red slab. Add them up and that's J, impact on the way out, risk while you hold, and a penalty on whatever is still on the book at the bell. Same shape of problem as the tank. Let's run the recipe on it and this time do the arithmetic in your head. Steps 1 and 2, fast. Write the Hamiltonian. The running cost is U squared plus 0.1 Q squared and the price times the motion is P times minus U. So H equals U squared plus 0.1 Q squared minus PU. Differentiate with respect to U. The U squared gives 2U, the minus PU gives minus P. So dH by du equals 2U minus P. Differentiate with respect to Q. Only the 0.1 Q squared has a Q in it and that gives 0.2 Q. And P dot is minus that. P dot equals minus 0.2 Q. Finally, the cost at the bell, 10 Q squared. Differentiate it with respect to Q and you get 20 Q. So P at 1 equals 20 times Q at 1. That's it. Same 3 objects, same 3 lines, and you've seen this shape once already. Steps 1 and 2 ticked. 4 steps left and we can do all of them in our head. Step 3. Guess U equals 1. Then Q dot equals minus 1, a constant selling rate. So Q of T is 1 minus T, a straight blue line draining, and it hits 0 at the bell. Step 4. From the right. P at 1 is 20 times 0, which is 0. Green dot, right end. Substitute Q equals 1 minus T into P dot equals minus 0.2 Q, and P dot is minus 0.2 times the quantity 1 minus T. Start at the bell where P is 0 and integrate leftward. Which function does that? Try the quantity 1 minus T squared. Differentiate it. 2 times 1 minus T times minus 1, which is minus 2 times the quantity 1 minus T. We want minus 0.2, so scale it by a tenth. P of T equals 0.1 times the quantity 1 minus T squared. A violet parabola drawn right to left. 0 at the bell exactly as we were handed. 0.1 at the open. Step 5. dH by du is 2u minus p. Our guess is u equals 1, so 2u is just 2. Subtract the costate. 2 minus 0.1 times the quantity 1 minus t squared. 1.9 at the open. 1.975 in the middle. 2.0 at the bell. Almost flat and positive, so again sell slower. Step 6, and here the step size changes. Tau of 0.05, half of what the tank got. Take that on trust for 60 seconds. U1 equals 1 minus 0.05 times that whole bracket. Multiply through. 0.05 times 2 is 0.1 and 1 minus 0.1 is 0.9. Then 0.05 times 0.1 is 0.005. And because we are subtracting a bracket that already carries a minus, that one comes back as a plus. So u1 of t equals 0.9 plus 0.005 times the quantity 1 minus t squared. At the 3 marks, open, middle, bell, 0.905, 0.901, 0.9 flat. The flat line drops to 9/10 with a whisker of curve on it, and the shape has flipped from the tank. There, the correction drooped toward the bell. Here, it lifts at the open. 3, 4, 5, 6. All ticked, all in your head. Down again. The score starts at 1.0333. One lap and it's at 0.9466. Then it basically stops moving. 9456. And the floor it's heading for is 0.9454. After 3 laps, we are already inside 1,000th of it. 3 laps, not 400. Now the step size, and let's make that dilemma concrete on this very problem. Take tau equal to 0.3. One lap and the score goes up to 3.713. Up, we overshot the valley and landed on the far wall, and the meter turns red. Tau of 0.2, 1.967, still worse than where we started. Tau of 0.1, 1.073, better than the last two, but look where we began, 1.033, still above it, still uphill. 3 tries, 3 failures, and the meter is red for all 3. Only at tau of 0.05 does the number finally fall below where we began, 0.947, green. On this problem, the honest step is small, and there was no way to know that except by trying. And the loop settles on this. Q star at 1 equals 0.0891. You deliberately do not finish selling. That last sliver is cheaper to carry overnight than to slam into the close. Steepest descent on a back-tested schedule is the first optimizer a real desk actually runs. Put the 2 staircases side by side and you can see the method's personality. Different lengths, the tank crawls for hundreds of laps. The trading book is done in 3, but the same shape, a stone drop, then a crawl. Because near the floor, the gradient fades, so the steps you take shrink to nothing. Easy to start, slow to finish. And the flip side of that is a real strength. It's almost impossible to start badly. Kirk ran this same loop on a much bigger problem, a stirred chemical reactor with 2 states and a coolant valve, and he ran it 4 different ways. 2 starting guesses crossed with 2 step sizes. One run took 27 laps, another took 48, a third got there in 7, the last 11. Wildly different journeys, and every one of them landed on the same floor. Now look back at the recipe card. Only step 6, nudge against the red curve, is really up for grabs. Rolling downhill is one way to do that correction. There are 3 more. Re-aim the cannon and fire again. Variation of extremals. Snap the bent curve straight in one shot. Quasi-linearization. Fold the step onto a wall so you stay inside hard limits. Gradient projection. Same loop, different corrections. 6 steps. Write the Hamiltonian, take the 3 derivatives, guess and sweep the state forward, sweep the costate backward, read the red curve, nudge against it and go again. That's the whole method. We started with a tank we couldn't solve and a wall we couldn't press play on. We never climbed that wall, we walked around it. 1 forward sweep and 1 backward sweep at a time. 2 problems, 1 tank and 1 trading book. Both solved with nothing harder than integration and arithmetic you could redo on paper. No formula handed to us. No trick that works once. Numerical optimal control. Kirk, Chapter 6. Solve it by hand.